Hi all, this is Mr. Yeager for chemistry, looking at a brief topic on intermolecular forces. All right, we're not doing, sorry, this chemical nomenclature, ignore. This is in our bonding unit, the end of it. Very brief, just looking at the three different type of intermolecular forces, which we sometimes abbreviate as IMF, and where you just need to be able to distinguish when each one is occurring in a covalent bond. This is in covalent bonds, not ionic bonds. All right. Again, this presentation was made by another chemistry teacher who does an amazing job. All right, the types of bonds. So we kind of already went over when we did ionic and covalent. I mentioned this word in the bonding video. These two are called intramolecular forces, okay? So again, they are holding them within the compound itself. So here's your review. Ionic are metal, nonmetal. Covalent are made of nonmetals completely. Valence electrons are transferred in ionic, shared in covalent, and results is the ions are attracted in ionic. Covalent, they share the electrons, and then you can see my examples down below here. I have a metal and a nonmetal, a metal and a nonmetal, 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 making the covalent. All right, so that leads us to the fact that with covalent, okay, we are looking at just covalent here. While the bond is holding the atom inside of it together, like the two atoms together inside of it, these compounds then like to come together. So like water, it's its own little compound, covalent compound, but obviously it needs to pool together. We see that when it becomes a liquid. We see that when it's a solid. Okay. So again, this is occurring when it's solid and liquid. It is occurring a little bit when it's gas, but it's very brief, and we're going to see what type that is. Okay. So intermolecular forces, IMF, are attractive forces that occur between compounds. And because these are between compounds, they're going to be weaker, because instead of atom holding on to each other, you're talking about the whole compound and compound trying to come together. But these are very important because this will determine, kind of how I've already clued at this, is that it'll determine whether it becomes a different state of matter, solids and liquids, whether the boiling point will be higher or lower, and whether it will be soluble in water. Okay, whether it'll be able to dissolve in water. So what we need to talk about real briefly here is, in intermolecular forces, we're going to be talking about something called a dipole. And a dipole is when you have a bond or molecule with two charged ends. All right, one positive end and one negative end. So this is not a full charge. This is not a full ionic charge like -1, -2, -3, +1, +2, +3. We kind of call this a partial charge, but it's something due to the fact that we talked about polar covalent molecules, okay, compounds. It means that the electrons are not shared equally, so there might be a time where the electrons spend more time on one side than the other side, and they keep coming back to this side. And so a general negative partial charge, or a dipole, forms. We have a negative on one side and therefore a positive dipole on the other side. All right, so that's what we're going to be looking at as we go through these three types called London dispersion, dipole-dipole, and hydrogen bonding. Okay. Oh, sorry, got to get rid of my pen. There we go. All right, so we're starting off with London dispersion, which is the goofiest name. Okay. Is the attraction resulting from the temporary attraction between protons in the nucleus of one atom and the negative electrons of a nearby atom. That's a very long definition, okay? This is something where it's very brief, okay? And like it says, it can only occur over very short distances. This is the weakest of all the intermolecular forces. And I think we have a picture on the next page where I'll be able to kind of show this a little bit more. All right, let me double check. Yep, okay. But the biggest thing you need to know is London dispersion is the weakest, okay? It will only occur in nonpolar molecules, so this is one where they don't have the dipole, okay? And it will occur just for a temporary moment in nonpolar and noble gases. So London dispersion is the weakest between nonpolar or noble gases. So what we basically have here is you have your atom, and everything is very, very equally distributed. So it doesn't want to have any charge. It's a neutral atom. But what happens is when two of these atoms get close to each other, this positive nucleus, you can see right here, could slightly attract those negative electrons in the other atom. Now the overall atom is still neutral, but together, for just a brief moment, we all of a sudden have this negative dipole and this positive dipole. But this is very weak, and within a moment will break, and they're going to separate back their own ways. Okay? So it's very, very, very brief is the key thing I want to say. All right? But it does create a dipole, and then it goes away. Okay? This is different from a dipole-dipole force. This is the second one. Okay? This is actually where we have dipoles. So we have a permanent positive end and a permanent negative end to a molecule, to a polar molecule. All right? And so the key here is dipole-dipole is stronger than is stronger than London dispersion, and it occurs in polar molecules. So dipole-dipole is stronger. So that's where you get back to this picture. So this is supposed to be some molecule, and this is how it always is, where it creates a negative side and a positive side. It finds another molecule similar to that. Obviously, the positive and negative sides will attract, or they'll repel if they're on the same side. Okay? But this is always created, and is definitely stronger. Like these will hold together better. All right? Then we have hydrogen bonding. First and foremost, hydrogen bonding is a type of dipole-dipole attraction. So this is kind of sometimes confusing. Hydrogen bonding is dipole-dipole, but it occurs specifically when nitrogen, oxygen, or fluorine, which we try to use this little NOF acronym, when those three elements are attracted to hydrogen, then we create a hydrogen bond. Okay? And it's just because these three elements, nitrogen, oxygen, and fluorine, they have some of the highest electronegativity, and so these bonds are stronger than any other dipole-dipole attraction. Okay, so this is the strongest IMF, and they will produce very, very high boiling points, which is why we are separating them out. Okay, so you have an example here, H2O. H2O, I'll draw it out, forms a dipole. This side will be negative, this side will be positive, and so therefore, another hydrogen molecule, another water molecule will be attracted to each other based on those dipoles, and like this will just keep on going and going and going. Sorry, I'm making a bad D there. So if I drew another one. This is true if it was H and N. Okay, we have H3N as an example, or HF. I'll just use HF. HF, this is going to be negative, this is going to be positive, and you can just kind of keep on creating these all the way down, and they are attracting between molecules. Okay, and so forth. This is different from a dipole-dipole like H2S. Now, this is where it gets confusing. H2S looks very similar to what H2O does. This would be negative, this would be positive, and there would be an attraction between that hydrogen and another sulfur on another atom. But this is not as strong. This would be considered a dipole-dipole interaction. So you got to be careful. Hydrogen bonding is not just when hydrogen is in the element. It's when hydrogen is bonded specifically with NOF, N-O-F. And you got examples here. So that's what I'm trying to show. You can draw in the partial negative, partial positive, partial negative, partial positive, etc., and so on and so on. Okay? And that's it. So those are the three types that you just got to be able to be knowing how strong each one is. So H bond's the strongest, dipole-dipole's next, and then London dispersion, and then knowing what type of molecules are involved in each type. And that's it. Thank you.